Welcome. In this video we are going to see atomic orbitals. Introduction. As we have seen in the last video, shells are different energy levels in which electrons will be presented. Shells are around the nucleus and there are different types of shells like K, L, M, N. And shells are divided into subshells. Those subshells are called as orbitals, and there are different types of orbitals like s, p, d, f. This is the simple model of atomic structure. So the core is called nucleus. In the nucleus, protons and neutrons are there. The shells are around the nucleus. So the core is called as nucleus, and inside the nucleus protons and neutrons are there. The first shell is named as K shell, the second shell is named as L shell, and the third shell is named as M shell. Now we are going to calculate the maximum number of electrons in each shell. So to calculate the maximum number of each shell, there is a technique. The maximum number of electrons in a shell can be calculated by twice the square of shell number. By twice the square of shell numbers. Let's see with an example. Okay, first we are going to calculate the maximum number of electrons in the first shell. So we are going to twice the square of shell number, that is 1 square. So 1 square is equal to 1 only. So 2 ones are 2. So in first shell maximum 2 electrons can occupy. Next, for second shell. So 2 twice the square of the shell number, that is 2 square. So 2 2s are 4, 2 4s are 8. In the second shell maximum 8 electrons can occupy. As well as in the third shell 2 into 3 square, because the shell number is 3. So 3 3s are 9, 2 9s are 18. In the third shell 18 electrons can occupy. By using this method, we can easily find out the maximum number of electrons in each shell. Next, we are going to see the detailed data of each shell, which means we are going to see the subshells of each shell. To be more clear, the types of orbitals. In those types of orbitals, how many orbitals are there? In those orbitals, what is the maximum number of electrons that can be occupied? So maximum number of electrons. First we are going to see about the first shell. First shell is named as K shell. So the subshell for K shell is S, and in S orbital only one orbital is there. In one orbital electrons can occupy, because as per the Pauli's exclusion principle, in one orbital only 2 electrons can occupy, and those 2 orbitals are paired spins. So in one orbital maximum 2 electrons can occupy, and those 2 orbitals are paired spins. Paired spins in the sense that pair will be spinning in the opposite direction. On account of that, we are using this symbol to denote the opposite direction of that paired spin electrons. So in an orbital, if there are 2 electrons, those 2 electrons will be rotating in the opposite directions like this. If this electron is rotating in anti-clockwise, then the another electron will be rotating in the clockwise. Because as we know already, Electrons are negatively charged subatomic particles. So these two electrons are negatively charged. Two negatively charged subatomic particles will be having a repulsion. Due to that repulsion, both of them are rotating in the opposite directions, not in the same direction. Because of that only we are using this symbol to denote the opposite repulsion of the paired electrons. Next we are going to see about the second shell. Second shell is named as L shell. In L shell, the subshells are S and P. In S subshell there is only one orbital, and in P subshell there are 3 orbitals. So in each orbital 2 electrons can occupy. Totally 8 electrons can occupy in the second shell. Next, third shell. Third shell is named as M shell, and in M shell the subshells are S, P and D. In S subshell there is only one orbital, in P subshell there are 3 orbitals, and in d orbital there are 5 orbitals. In each orbital 2 electrons can occupy. So 2 plus 6 plus 5 to 10, totally 18 electrons can occupy in the third shell. Next we are going to see about the fourth shell. Fourth shell is named as N shell, and in fourth shell the subshells are S, P, D and F. In S subshell there is only one orbital, in P subshell there are 3 orbitals, in D subshell there are 5 orbitals, and in F subshell there are 7 orbitals. So 2 ones are 2, plus 3 twos are 6, plus 5 twos are 10, plus 7 twos are 14. Totally 32 electrons can occupy in the fourth shell. Next we are going to see the explanation for electronic configuration. We are writing the electronic configuration for each and every element based on the Aufbau principle. Now we are going to see the detailed explanation for that. The energy level of each shell is increasing in this order, which means 1s is the lowest energy level, so the energy is increasing on the higher side. While writing the electronic configuration, we are writing 3 terms altogether. Now I will tell you what is the meaning of those 3 terms. First we are writing a number. So the numbers are denoting the shell numbers. The numbers denoting the shell numbers. And next we are writing the letters S, P, D, F. These are all denoting the subshells, which means the type of orbitals. Subshells, which means the type of orbitals. And finally we are writing some numbers on the power of the subshells, and those power values are nothing but they are the maximum number of electrons that can be occupied in those subshells. Next we are going to see the energy level comparison of shells using graphical method. In x-axis I am going to take orbitals, and in y-axis I am going to take the energy level of those orbitals. As we know already, 1s is the lowest energy level in an atom, so 1s should be written on the bottom of the y-axis to denote it is the lowest energy level. And in 1s there are 2 electrons. Those 2 electrons should be written like this based on the Pauli's exclusion principle. Next, second shell. In second shell there are 2 subshells. They are 2s and 2p. First one 2s. In s-type subshells only one orbital is there, so maximum 2 electrons can occupy. 2s is energier than the 1s orbital. And there is another subshell, that is 2p. In p-type subshells, there are 3 orbitals, so maximum 6 electrons can occupy. Even 2p is energier than the 2s orbital. Next, third shell. In third shell, there are 3 subshells. First one, 3s. 3s is energier than the 1s, 2s and 2p. So in s-type, there is only 1 orbital, so 2 electrons maximum can occupy. The next subshell is 3p. In 3p, there are 3 orbitals, so maximum 6 electrons can occupy. And there is one more subshell in third shell, that is 3d. In 3d, there are 5 orbitals, so maximum 10 electrons can occupy. So the energy is increasing in this order. From this we can come to understand that the energy difference is there in both subshells and shells. The energy level difference is increasing in this order from S to F. As well as in shells, it is increasing from K to N. That means from first shell to the fourth shell. Next, we are going to learn how to write the electronic configuration. So electronic configuration is nothing but arrangement of electrons in the orbitals. Let's see with an example. First, we are going to learn how to write the electronic configuration for carbon. So the atomic number of carbon is 6. Atomic number is nothing but it is the number of protons in carbon atom. So the electronic configuration of carbon is 2, 4. So first energy level is 1s orbital. In first orbital there are 2 electrons. In second energy level is 2s. In 2s 2 electrons. And in 2p remaining 2 electrons will occupy. In 2p maximum 6 electrons can occupy, but in the case of carbon remaining 2 electrons are there, so those 2 electrons will occupy in the 2p orbital. First energy level is 1s. In 1s there is only 1 orbital. Next energy level is 2s. In 2s also there is only 1 orbital. Next energy level 2p. In 2p there are 3 orbitals. 2p there are 3 orbitals, because already I told you that in s-type there is only 1 orbital, in p-type there are 3 orbitals. And also I told you that in each orbital maximum 2 electrons can occupy based on the Pauli's exclusion principle, and those 2 electrons should be written like this to indicate that the repulsion force between those 2 electrons and they are rotating in the opposite direction. So in the first 1s2 orbital there are 2 electrons. In the second 2s orbital also there are 2 electrons. But in 2p there are 2 electrons. Those 2 electrons should not be written like this, because electrons like to accommodate separately without pairing with any other electrons. So the second electron will accommodate in the second orbital instead of pairing with the first electron in the first orbital. This is the correct way of writing the electronic configuration of carbon atom. Now we are going to see another example for writing the electronic configuration of chlorine atom. For chlorine, the atomic number is 17. The electronic configuration of chlorine is 2, 8 and 7. Those 2 electrons will accommodate in the first shell. And these 8 electrons will accommodate in the second shell, and those 7 electrons will accommodate in the third shell. The electronic configuration of chlorine is 1s2, because for the first shell s is the subshell, and for second shell there are 2 subshells, they are 2s and 2p. In the s orbital 2 electrons and p orbital 6 electrons maximum can occupy. In the third shell, first subshell is 3s, so in 3s 2 electrons will occupy, but there are 7 electrons in the outermost orbital. 2 electrons occupied in the 3s2. The remaining 5 electrons will occupy in the 3p subshell as 3p5. So let's see how to fill these electrons in the orbitals. First orbital is 1s, and next 2s, And the next orbital is 2p. In p-type there are 3 orbitals, and next 3s, and finally 3p. So in 1s, 2 electrons will occupy, and in 2s also 2 electrons will occupy. In 2p, 6 electrons will occupy. The correct way of writing electronic configuration, this is only. In 3s also 2 electrons. In 3p, as same as in carbon, we should write like this only, because the electrons will like to occupy without pairing. So that's why we are saying that chlorine needs one more electron to attain the octet state, because in 3p there is only one electron is there in the last orbital. Next chapter that we are going to see is shape of atomic orbitals. There are different types of atomic orbitals like s-orbital, p-orbital, d-orbital and f-orbital. Let's see one by one. First one, s-orbital. The shape of s-orbital is spherical. S-orbital is in spherical shape. Spherical in the sense the s-orbital looks like a ball. First lower energy s-orbital is 1s orbital, which is in the first shell. So 1s orbital looking like this, because as per the Heisenberg uncertainty principle, electrons do not have a definite shape, but instead they will be in diffused state. So orbitals also can be visualized in diffused state. Orbitals also can be visualized in diffused state. That's why we are drawing the shape s orbital like that. So the lower energy level s orbital is 1s orbital, and s orbital is in spherical shape. The next energy level s orbital is 2s orbital. 2s orbital is bigger than the 1s orbital. Due to the diffused state of electrons, orbitals can be visualized in the form of charge clouds. So orbitals can be visualized in the form of charge clouds. There are 2 electrons in the first shell, because in 1s maximum 2 electrons can occupy. In the 2s also 2 electrons can occupy. Between the 1s and 2s orbitals there is a zone called nodal zone. This zone is called nodal zone, and in nodal zone the probability of finding the electrons is 0, which means there will not be any electrons in the nodal zone. So nodal zone is nothing but it is the zone between 1s and 2s orbitals. In nodal zone there is no probability of finding an electron. Next, shape of p orbitals. The shape of p orbitals is dumbbell shape. So p orbitals will be looking like this only. And in p-type subshells there are 3 orbitals. They are called as px, py and pz. The first orbital is named as px, the second one is py and the third one is pz. Let's see one by one. In 3-dimensional there are 3 axes, x, y and z. This axis is x and this is y and this one is z. In 3-dimensional this will be x axis, this will be y axis and this one will be the z axis. In 3-dimensional 3 axes will be like this only. The dumbbell shape px orbital will be on the x axis. So px orbital will be on the x axis. Next one, py. Py dumbbell shape orbital will be on the y axis. This is x, y and z. The py orbital will be on the y-axis. This is py. And next one is pz, and z orbital, pz orbital will be on the z-axis. This is the shape of pz orbital which is on the z-axis. Now we are going to see these three orbitals together. This is px orbital, and this one is py orbital, and next one is pz orbital. Now it is little bit confusing, right? So this is the px orbital, and this one is py orbital, and the next one is pz orbital. In 3D, these three orbitals will be looking like this only. This is the structure of p orbital. But when we look at each orbital, there are two axes which are not having any planes. In px, y and z, in py, z and x, in pz, x and y. These are all called nodal planes. So in px, y and z, in which there is no probability of finding an electron. So these are all called nodal planes. Then for py, z and x are the nodal planes. So these two axes are the nodal planes of py orbital. Next, in pz orbital, y and x are the nodal planes. So in pz, nodal planes are x and y. Now we are going to see the shape of d orbital. In d-type subshells, there are 5 orbitals. The first d orbital is named as dxy. The second one is dyz. Third one is dzx. Fourth one is dx2 minus y2. And the last d orbital is named as dz2. It is named as dz2. So the shape of first 3 orbitals is clover leaf shape. These 3 orbitals are in clover leaf shape. The last dz2 orbital is symmetrical about the z-axis. It is symmetrical about the z-axis. Whereas dx2 minus y2 orbital also is in clover leaf shape. But the difference between first 3 orbitals and the dx2 minus y2 orbital is it will be along the axis, whereas these 3 orbitals will lie in the axis. They will lie in the axis. Now let's see the shape of these 5 d orbitals one by one, then only you can understand. As I told you already, the dxy orbital will lie in x and y axes. So they will lie in x and y axis like this. This is the shape of dxy orbital. Next, the shape of dyz orbital. So it will lie in y and z axis. So it will lie like this in x axis and y axis. This is the shape of dyz orbital. Next one is dzx orbital. So it will lie in z axis and y axis. So the shape of dzx orbital is like this. This is the shape of dzx. Next one is dx2 minus y2 orbital. As I told you already, the dx2 minus y2 orbital is along the x-axis and y-axis. So it will be along the x-axis and y-axis like this. This is the shape of dx2 minus y2 orbital. And next one, the last one, dz2 orbital. So the dz2 orbital is symmetrical about the z-axis. The shape of dz2 orbital will be like this. This is the shape of dz2 orbital. These are the structures of d subshell. Thank you for watching this video. We'll see you in the next video. Thank you.